The intermediate value property then, f is continuous on the interval ab. For every real number gamma between fa and fb, there exists a number c between a and b such that f of c is equal to gamma. So basically we're going to look at the second part of this proof here. This result claims that if f is a continuous function, takes the values fa and fb at the endpoints of some interval ab, then f must take all possible values between a and b, fa and fb. Okay, that's what it's saying then, the theorem. Let's go down then and we'll scroll down to where we are. We actually showed that c, so we'll have a look at what c is a moment. We showed that c was is between a and b. So where was it defined? C was equal to the supremum of this, where f of is the x's in AB, such that the f of x's are less than gamma, where gamma belongs to AB, and we've shown that the C, which is the supremum of S, the biggest value in this, the supremum, the least upper bound of this set, which is labelled C, lies between A and B, is what we've shown so far. So now we're going to go on from this proof now in the second part. Let's have a look at it then. Here it is here. So since C lies between A and B, we now use the fact that f is continuous at C to show that the possibilities that fc is less than gamma and fc is greater than gamma are impossible. So if these are both impossible, the only conclusion that we can then take is that fc must equal gamma. And that, what would that mean? Well, we'll look at that in due course. I'm not sure what that would mean at the moment. Just go back up, just remind myself. fc equals gamma. That's what we wanted to show, didn't we? That there exists a c in between a and b, such that fc equals gamma. So that's what we're actually heading for. Okay, that's good then. So let's have a look at this then. So case 1, if this holds here, then we can define gamma minus fc is greater than 0, so let epsilon be that, which is greater than 0. F is continuous at c. There exists a delta, such that if x lies in here, then the f of x's lie in here. Choose delta sufficiently small, such that delta is less than the min of these values, in order that the condition guarantees that x is in AB. Okay, here, if we look at this, a is less than we look at x, first of all, for this, will be between c plus delta and c minus delta. And here, if we look at delta being smaller than this, c will be, delta would be smaller than a minus c, c minus a rather. If we move this around, we get this part. And on this side, we can see that delta would need to be smaller than b minus c. So taking delta to be the minimum of these two, c lies between. So if we just look at that on the number line, here's a, here's b, and c lies somewhere between. And we're taking delta to be smaller than the smaller difference of the two. The c minus a is this distance, and the b minus c is this distance. And we're making sure, ensuring that the delta either side of c is within the said region AB. That's all this is. So we need to make it sufficiently small. Okay, good. That's good. So this is fine. Then in particular, so if this holds, then c plus half delta is in here, isn't it? Okay, that satisfies this condition here. It'll be in between these two. C plus half delta will be in here. So it satisfies this inequality, of course. So that's less than epsilon. And so, what have we got? Let's have a look then. Replace this epsilon by gamma minus fc, and just take the positive quantity of the modulus then here, which we can write here. And we've got this minus this then is less than epsilon, because both this value and its negative are less than epsilon. So we can just take this value here, and that's less than gamma minus fc. The fc's cancel, and we see that fc plus half delta is less than gamma. So c plus half delta is in S, which contradicts the fact that c is the supremum of S, because c was the biggest value, wasn't it? C was the supremum of S, and we found a value c plus half delta, which is in AB, and where f of c plus half delta is less than gamma. So c plus half delta would be in S, but c is the supremum of S, so that's a contradiction. So clearly this is impossible then, the first thing. Now case 2, let's assume the other ways around then. Fc is bigger than gamma. So we'll take our epsilon now to be Fc minus gamma, which is positive. F is continuous at C, as we said before, so there exists a delta sufficiently small, such that if x lies in here, then this condition holds. Choose delta such that delta is less than this thing again, for the same reasons as before. It now follows that for any x satisfying x on the left-hand side of C, up to including C, so that's fine, any x in here, on the left-hand side, then we know up to C, yeah, then we know that this, so here we can take fx minus c, fc is less than that, epsilon is equal to this, fc minus gamma, which we've put in, but this implies then flipping the modulus around, so I'm going to write the minus value of this. Fc minus fx will still be less than that. Okay, because it's both this value and its minus are both less than this when we say the modulus is. So we can flip it around and run a minus through it. It's less than this. The fc's cancel, we see f minus fx is less than minus gamma, so fx is greater than gamma, which we've got here. Here we see that none of the x is in the range then, because x satisfied this condition here, lie in S. None of the x's here, because they're all f of x is greater than gamma, lie in S. So C is not a supremum of S, is it? If they all lie in, none of these x's lie in S. So C can't be a supremum then, because this segment doesn't lie in S. But this is a contradiction, because C is the supremum. Consequently, f of c greater than gamma is also impossible. Therefore, the only conclusion that can be drawn is that fc equals gamma. And so gamma is a value of f as required. So we found that c there. And that completes the proof.